All right, we're going to switch gears here a little bit, kind of get away from the polynomial quadratic thing, and we're going to take a little bit more of a look at exponential functions, logarithmic functions, and stuff along those lines. Now, you should have been introduced to these types of functions at some point in time in Algebra 1, but if you weren't, it's kind of one of those things where it's a nice change of pace, because they're a little bit different than what we've been working with before, and they're a little bit, what I would call simpler in comparison to some of the stuff that we've talked about earlier in the year. Okay, what we're going to do in this particular section is we're going to write and evaluate exponential expressions to model growth and decay situations. All right, now that might not make a whole lot of sense to you right now, but as we move forward here a little bit, this objective and the terms that we're looking at right here are going to make a lot more sense to you. Okay, so we're going to talk about what an exponential function is, what the base of that exponential function is, what an asymptote is, and also how to be able to tell the difference between exponential growth and exponential decay. Alright, so what this does is it starts off with kind of a brief example. There's a rule used in the computer industry that states the number of transistors per integrated circuit doubles every year. Alright, now the whole scenario itself really isn't that important, but what we're getting at here is as each year progresses, as you can see in the model down here, as we move from year to year, okay, we add 1 year each time, you can see how the number of transistors, or basically your output, doubles each way all the way across. Okay, the reason we bring this up to start with is this is a really good example of an exponential function. Okay, things are increasing in this case at an exponential rate. Okay, so growth that doubles every year can be modeled by a function with a variable that's in the exponent. All right, now everything that we've talked about so far, the variables have been, the bases of exponents, or the variables have been, with other constants, but nothing to the point where the variable has actually been an exponent. All right, well, basically that leads us to what an exponential function really is. Okay, right here in the middle of your screen is kind of your parent function, so to speak, a generalized version of what your parent function is going to be, where the base, which is the b in this case, is represented by some type of number, okay, a constant number. So for example, what we're going to look at here in a second would be something like this, okay, where your variable actually happens to be the exponent. It's not anything to do with the base. Okay, now on the bottom down here, it just does another pretty good job here of explaining, okay, the base and the exponent, and showing that the exponent is actually going to be our variable. Okay, the key here is that your base right here is usually some number that's greater than 0, but it's never going to be 1, because obviously if it's 1, it doesn't matter what power you would raise it to. Okay, 1 to the first, 1 to the second, 1 to the third, you're always going to get 1. So that really wouldn't show any growth. But usually b is going to be a positive number. Now there's ways that we can, affect something like that, or, adjust it a little bit so b doesn't always end up being a positive number, but usually that's by introducing some other type of negative number in front of it. So for the most part, b is always going to be a positive number. Okay, now the example that I just alluded to on the previous slide, okay, f of x equals 2 to the x. Okay, it's graphed over here on the right side. Okay, we are going to talk a little bit about domain and range here. Okay, now remember, domain refers to your x values, range refers to your y values. As far as how all this is going to work, usually domain is something that you can tell ahead of time, just by looking at the function itself, or looking at the part that I have boxed in right here. As far as the range goes, usually you need to be able to look at the graph of a particular function to see what y values actually show up. Okay, so something that you want to remember here, the domain of an exponential function is always going to be all real numbers. Okay, so there's a lot of different ways that you could probably write this if you really wanted to. Sometimes you're just asked to write down all real numbers, and it's kind of a goofy looking R that kind of has like two lines behind it, okay, or two lines that make up the base of your R. Okay, so that just represents all real numbers. You could specifically state that it's going to be all real numbers, or sometimes you'll see something written like this in interval notation, negative infinity to positive infinity. That also just means any single number could be a part of the domain of that particular function. Okay, now the range, you'll see it written like this up here. What this is saying is y, this line in the middle basically just means such that. So y such that y is greater than 0, or meaning that y has to be some number that is greater than 0. Alright, so what you'll notice about the graph on the right is the y values that show up on the graph are always going to be greater than 0. They never actually touch 0, and they never go below 0 in terms of an x direction. Alright, we'll talk a little bit more about that in a little bit. And that could be kind of represented in a similar fashion if you're talking about all your y values, okay, being greater than 0. Okay, but we'll get into that a little bit more as we go. Now, the one thing that we're going to have to make sure that we kind of review a little bit here is what happens to exponential functions when you start filling in negative numbers. Now remember, when we worked with exponents before, okay, say I have 2 and I raise it to the negative 2. Alright, well, first of all, a negative exponent always tells you that you have to flip something. Okay, if it's on the top, it would basically go like this. You bring it to the bottom to make it positive. And then we would go ahead and take 2 to the second, which is 4. So we get 1/4, which you can see down here. So you do have to work with fractions a little bit when you do this. Okay, and understand what negative exponents mean. If your base starts out as a fraction, and say that's raised to a negative 2, okay, well again, it's in the bottom, so you have to make your exponent positive first, which would mean bring it to the top, and then evaluating from there. Okay, so the first things first, you just have to understand what it means if you have a negative exponent. Alright, now as far as graphing these goes, we can use graphing calculators to graph them, which is probably the easiest way. If you were asked to do it by hand, it's one of those things where you're just going to take x values, okay, around this version or area of the graph, and you're just going to fill them in, and you're going to evaluate to find the y value that goes with it. Alright, so it's not really anything different than what we've done when we've graphed things kind of longhand before. Alright, it's just you might end up with some kind of, it's a different situation or a different scenario as far as filling in different values. Okay, now, same graphs here on the right. Okay, again, just kind of want to talk about what's going on here. We already talked about the domain being all real numbers, and in this case, your range goes from 0 on up to infinity. Okay, or basically anything that is greater than 0 is going to show up on your graph if we were to continue to take this out. Now, here's the thing here about it never ever touching 0. Okay, on the previous slide you saw when we have our function, we filled in negative 2 and got 1/4. Now you can see as we continue to fill in negative numbers, say we're going to take and fill in f to the negative 5. So we're going to fill negative 5 in where there's an x. Okay, well we'd have to flip it to make that positive. Now 1 over 2 to the 5th is just going to be 1 over 32. Okay, so again you can see that we still have a number, alright, and we're never ever going to get 0 by filling in an x value for this. Okay, the more negative you continue to go, okay, the more we tend to go this way as far as filling in x values. They're going to be larger negative numbers, but again, what it's going to do when you fill in the negative is it's going to have to flip your number over, and you're just going to get a really, really small fraction, or a fraction with a very, very large denominator. So as this line, as you can see here, continues to go out here to the left towards negative infinity, alright, the numbers that it represents as far as outputs are going to be very, very small fractions, or fractions with very, very large denominators, but you're never ever going to get to 0. So this line, as we continue this way, continues on forever. It's going to get super close to 0, but it's never ever going to actually touch 0. Okay? So what is explained down here with this underlined term is that means y equals 0, okay, or the horizontal line that's kind of dotted up here in green, and I'm dotting over the top of it, y equals 0, is referred to as an asymptote. a horizontal asymptote. And what an asymptote is, it is an imaginary line on your graph that your function approaches and gets really, really close to, but never actually physically touches. So like I said, as our graph continues to go out here to the left, all right, we're going to get really, really close in terms of a y direction of touching 0, but we're never ever actually going to touch it. Okay, so that makes 0 a horizontal asymptote, or the line y equals 0. Remember, horizontal vertical lines, y equals something represents a horizontal line, because every point on that line would have a y value of 0. Okay, if you had x equals something, that represents a vertical line, because every point on that line would have the same x value. Okay, so that's just kind of to get us started here a little bit as far as what exponential functions are, how they operate, all that fun stuff. Again, as far as graphing or trying to get output values out of them, it's just a matter of filling in x values and coming up with points or to determine those output values or those y values. All right, now the next thing we're going to talk about here is how you can tell if something's going to be a growth model. Okay, is it going to go up like the last graph did as we move over, or is it going to be a decay model? Is it going to look something like this? As your x values get bigger, is it actually going to decrease? Okay, and basically what it comes down to is we said that b, the base of our function, is always going to be a positive number, but a is going to dictate to us whether we have a growth function or a decay function. Okay, so if the a is greater than 0 and b is still greater than 1, like we talked about before, you're going to see growth. Okay, or basically the function is going to increase, like I have over here on the right, as we move this way on the x-axis. Okay, when b is between 0 and 1, okay, it's still going to be positive. Okay, the function is going to be exponential decay instead. All right, and that's going to be more an example of what we talked about on the left over here. As your x values increase, the graph itself or the function is going to decrease. Now, if that didn't make a whole lot of sense to you, that's okay. It's one of those things where sometimes it helps just to be able to see things to get a better idea. Okay, now just a couple reminders here as we move forward. Remember, we've been talking about f of x equaling b to the x. All right, something along those lines, an exponential function. Remember, f of x and y are more or less interchangeable, and this is just making sure that you remember that y depends upon the x value. Okay, so we're still talking independent versus dependent variable stuff, where the x, even though it's an x variable that's in a place that's a little different than what we normally talk about, it's in the exponent area, it's still independent. We can put whatever we want to in for it. Right, and the y value, or the value of the function f of x, depends upon that value. Okay, so the y is still dependent. On the bottom, this is some stuff that we talked about already as far as understanding what happens when you have negative exponents, how you have to first make them positive, and then kind of go from there. All right, now we're going to take a look at this right here. It says tell whether the function shows growth or whether it shows decay. All right, so what we're looking at here is, all right, more or less what's in parentheses. Okay, the 10 is positive. That's more or less the base of my function. Okay, 10 to the x would kind of be like my parent function in this case. All right, but what we're going to look at is on the inside here. If this number in here is less than 1, okay, or between 0 and 1, what that's going to do is that means that as our graph moves to the right, this 3/4 is actually going to cause our values to decrease. So what we're looking at here is if this number in here is less than 1, all right, it's an example of decay. Okay, so that's really all the thing we have to do to start with is it growth or decay? Well, in this case, because this other number in here beside my base is less than 1, yet greater than 0, all right, it's going to be decay. Now, it did say to graph things. As far as graphing goes, in this particular case, again, we're just going to start by picking x values, filling them in to the function up here, okay, and then evaluating and seeing what comes out, which I've already done here in this particular table that happens to be here, and the graph on the bottom can already be seen. Now, it's one of those things, again, if you have access to a graphing calculator and you're supposed to graph something, I don't have a problem with you using that, but you still need to understand, okay, that points such as the points that are in this table on this particular example can be found by taking these x values and filling them in for the x, in this case the exponent, and evaluating. Now, some of them are obviously easier than others. In this case, because it's a decay model and this number in here is a fraction, well, when we fill in 0, anything to the 0 power is just going to be 1. So essentially this whole part right here just turns into 1. So 10 times 1 gives us that output value of 10. But when we start filling in values like 2, okay, now all of a sudden, if you take 3/4 and you raise it to the second, now you have to square the top, square the bottom, and essentially get 9 over 16, then take 9 over 16 times 10. And then all of a sudden you end up with, 90 over 16. We're getting to the point where then you probably have to use a calculator, or you'd be better off maybe just taking the whole thing itself and filling it into a calculator and getting decimal numbers for your output values. But the main point here is if you had to graph it, you could graph it using a calculator or by filling, input values in for x and using a calculator to find output values even if they are decimals. The big thing here is if you look at the graph, you're able to understand that it decreases or it's going down as we start moving this way. So that means that we have a model that represents decay. Okay, same idea here. The base, or the b that we've been talking about most of the time, is this 100 right here. All right, but we're going to look inside at this other factor. In this case, it's greater than 1. So because it's greater than 1, that tells us that we have something that models growth. Okay, now again, if we wanted to graph this, we could start picking random x values, filling them in here, all right, and basically taking 1.05, raising them to a specific power, and then multiplying by 100. You could get a list of values that would be on your graph, or a list of points that would be in your graph. But again, in this case, because it's a decimal thing, using a graphing calculator would probably be your best bet, or using a calculator at any point just to help you figure out those output values would probably be your best bet. Okay, so there's a couple different means or methods that you can use when you're going to have to graph some of these today on your assignment. Okay, but the main thing is, again, it increases as we're moving this way. Okay, so it's an example of growth. So being able to tell the difference between growth and decay is kind of the first part of what we got going on here. All right, so if you want to take a little break, maybe take a look at your assignment. See if you can get through some of those growth and decay problems as far as determining the difference between the two. Maybe even getting some graphs up there. Now would probably be a pretty good time to do that. Okay, and then when you come back, we'll start with the second part of the assignment here. All right, now the next part, we're just going to kind of take all this growth and decay stuff, and we're going to kind of apply it to some, basically some interest type problems. Okay, so this is what we're looking at. This is going to be a function, or a generalized version of a function that's given to you, that's going to help you figure out basically what the final amount of something would be after a specific number of time, or a specific period of time, with a specific increase or decrease in the rate applied to a specific amount. Okay, so the main thing here is you're going to take your initial amount, fill it in for A. You're going to take 1, and you're either going to add the rate to it, or you're going to subtract the rate to it, depending on whether it's going to be growth or decay. And then T up here, or you can represent it as X, whichever way you want to do it, is going to represent kind of your exponential growth or decay time frame that we're looking at right here. And the final amount that we want to get is going to be our output value. Okay, so basically it's just one of those things where we can also use a graphing calculator, which we're probably going to use here, because when we start talking about really large starting values like $5,000, and we're applying a growth of, in this case, this would represent like 6.25% over some specified year amount. Okay, what we're probably going to be asked to do is figure out, okay, if we start with $5,000, after so much time, okay, or after what time frame are we going to equal $8,000? So really what you should be looking at is you're trying to figure out what value of X is going to give you an output value of $8,000. So the only way to figure that out is going to be by looking at a graph and figuring out in terms of outputs or Y values, where does it look like your graph reaches 8,000? Okay, so we're going to apply this a little bit here. Okay, so Clara invests $5,000 in an account that pays 6.25% interest per year. After how many years will her investment be worth $10,000? Okay, so what we're looking at here is, again, my final amount, which was represented like this on the previous slide, A of t. Okay, we want to take our initial amount, which is $5,000. All right, and then because it's supposed to grow, all right, it's going to be 1 plus, we take our percentage and we actually represent it as a decimal. So 0 point is going to be 0.625, and then our exponent would still be a t up there. Okay, so more or less the function that is going to represent the growth of this money or the growth of this investment is going to be 1.0625 to the t. Okay, so again, because it's growth, or we know that our investment is going to increase, we add the rate, okay, which we always take our rate and we go from a percentage to a decimal. Okay, so we add that to 1 and get this value in here. So it's going to represent a growth model, again, because this number in here is greater than 1. Okay, so what we would do at this point, if we actually want to figure out when it's going to be equal to $10,000, okay, we'd have to go ahead and graph this, okay, because we really haven't talked about ways to go ahead and solve for the t up here, algebraic ways to solve for the t without graphing. So what we would do is we would take that and we'd graph it on a graphing calculator. Okay, so the function that we just came up with, we graph on a graphing calculator, and then we can take our trace button that's on our calculator, which basically gives you a cursor that follows the line of the graph. All right, and you can see here, as we move to the right, our value is going up. Okay, and what we would do is we'd take and we'd move that cursor to a point where it looks like we're around 10,000 for our Y value. Okay, and we'd look at what X value happens to coordinate with that or correspond to that. Okay, so in this case, it looks like it's one of those deals where after about 12 years, okay, right here, after about 12 years, my output value would equal right around $10,000, give or take. Now, obviously, we can only approximate in this case. Okay, we can only approximate that it's going to be closer, and we're looking at total year values anyway. We don't really want to have like 11.97 of a year. That doesn't probably help us out in this context a whole lot. So we'd be looking at more of an estimate of what's going on. You could also use the table that's built into your graph, table feature. And again, the X values, or basically the T values, all right, would correspond to different years. Okay, so again, after approximately 12 years, the value of the money would be right around $10,000, just a little bit more. If you wanted to be more specific, you could go ahead and actually figure out that the year value would be like 11.43. There's some other things that we can do on the calculator to make that work, but that's one of those things that we'll probably discuss in class. Okay, now we're going to take the same type of situation here. It says the city population, which was initially 15,500, has been dropping 3% a year. Write an exponential function and graph the function. Use the graph to predict when the population will drop below 8,000 people. Okay, so again, our initial value, and I'll just go A of t again as far as our function goes. And you could change it to like P of t if you wanted to, just because it's population as opposed to something else. But 15,500, 1, and then in this case we're decaying. So 3% as a decimal would be 0.03. And then our time frame up there again would be t, which is representing each year that this would progress. Okay, so our final function would be 15,500 If we take 1 minus 0.03, we'd get 0.97 t. Now again, this would make sense because if it's supposed to be decay, you should be getting a number inside parentheses that looks like that. Okay, less than 1. So this is going to represent a decay model. Now once you get to this point again, we don't really have the means algebraically to figure out what t is without graphing it. Alright, so we're just going to graph the function. Okay, so when you use your variable on your calculator, again, t is going to turn into an x. Okay, so we graph it. We'll use the trace function again to get our cursor on the graph line somewhere. Okay, and then what we're going to do is, again, when is the population going to fall below 8,000? Okay, well, basically we just have to move along that graph, all right, until we get something that falls below 8,000. So again, this is going to be an approximation, but approximately 22 years from the time we did this to the time we were trying to find it fall below 8,000 is when it would actually fall below 8,000. Okay, so again, approximately 22 years. And for right now, an approximation does enough for us in terms of what we're trying to find. All right. So again, there's not really a whole lot to this assignment. If you can tell the difference between exponential growth and decay, and then be able to fill in some values to a particular function to be able to graph it, or use a graphing calculator to graph it, and then kind of take the whole idea of growth and decay and be able to apply it to a specific situation, is pretty much all that's to it. So get started on your homework. Make sure you come to class with it ready to go, and some questions, and makes things a lot easier in the classroom portion of everything that we're trying to accomplish.